Last time we managed to reconstruct a signal out of the individual sine waves that make it up, just as the inverse Fourier transform does. If you missed that video or any in this series on fixing your FFT, you can find the whole playlist by clicking on the info card up there in the corner. But when we played the signal back, it was only half as loud. We were missing half the energy in the signal. Where is the energy gone? Have we made an error in our calculations? There's no error. We're just not seeing the whole picture. The answer to where this missing energy has gone has to do with a strange number whose existence had been suspected since the time of Heron of Alexandria in the 1st century AD, but whose nature was only really defined in the 16th century by Italian mathematician Raffaele Bombelli. That number is the square root of -1. The whole idea that a minus number could have a square root was so despised by mathematicians that in the 17th century René Descartes even gave it the rather unfortunate name by which we know it today, an imaginary number. It wasn't until Leonhard Euler used it in his famous formula in 1748 that the square root of -1, or as it is known to most people nowadays, I, gained widespread acceptance as a fundamental concept in mathematics. What does all this have to do with the energy missing from our signal? To find out, we have to delve a little deeper into the world of complex numbers. Whereas the regular numbers we all learnt at school, let's call these the real numbers, lie on a single number line that stretches from -infinity to +infinity, passing through all the negative numbers, positive numbers, integers and decimals in between, imaginary numbers occupy a completely different number line in quite a different or imaginary dimension of their own. When we put the real and imaginary number lines together, they form what is known as the complex plane. Any point on this plane can be described by a complex number. A complex number is made up of two parts, a real part and an imaginary part. The real part tells us the position of a point on the complex plane along the real axis, and the imaginary part tells us its position on the imaginary axis. Therefore, this point here can be described by the complex number 3 plus 4i. What happens to the real number 1 when we multiply it by I? It gets rotated by 90 degrees onto the imaginary axis and now equals I. What happens if we multiply it by I again? It gets rotated another 90 degrees back into the real axis, but now it equals -1. This is why I squared equals -1. In 1748, the Swiss mathematician Leonhard Euler used I to give the world Euler's formula, which states that e to the ix equals the cosine of x plus I times the sine of x. E is Euler's number, 2.71828 and so on. Raising Euler's number to x, where x is any real number, gives us a graph that looks like this. What does raising e to the ix look like? Euler's formula tells us that in the real dimension it looks like a cosine wave. But what has multiplying by I done to the sine wave? It's rotated it into the imaginary dimension. If we add these two functions together for all values of x, we get a three-dimensional helix. This is the complex exponential e to the ix. When we look at it from the real dimension, it looks like a cosine wave. But when we look at it from the imaginary dimension, it looks like a sine wave. Combining cosine and sine waves in this way was perfect for Fourier, as he now had a way of combining the cosine and sine parts of his calculation into one neat expression. So you'll very often see the Fourier series expressed in terms of the complex exponential. Just why e to the ix is equal to a real cosine wave plus an imaginary sine wave has to do with the way that Euler's number, the sine function and the cosine function are all calculated. The thing about complex numbers is that by the time Fourier perfected the Fourier series in 1822, Bombelli's rules of how to work with them had been around for some 250 years. So even though the concept of complex numbers might have seemed mysterious or even nonsensical at times, a solid foundation of algebraic rules for manipulating them was well established, which was essential for the Fourier series. One of these rules is known as the complex conjugate, and predicts a property of our signal that will help us to find the missing energy. In fact, the complex conjugate was one of the triggers that had spurred the development of complex numbers in the first place, culminating in Bombelli's work. In 1543, Girolamo Cardano was trying to solve a problem called the depressed cubic, when he found himself looking for two numbers that when added together made 10, but when multiplied made 40. Despite calling it torture in chapter 37 of his seminal work Ars Magna, he attempted the feat anyway, and came up with the solution 5 plus the square root of minus 15, and 5 minus the square root of minus 15. These two numbers are complex conjugates. When we add them together, the square root terms cancel, and we get the answer 10, a real result. Similarly, when we multiply them, the square root terms again cancel out, and we get the answer 40, which is also a real result. But Cardano was unconvinced by his feat of mathematical jiggery-pokery, and called his solution useless. It was only picked up again some 30 years later by Bombelli. However, for us, the complex conjugate is extremely useful. Our signal is real. That is to say, its amplitude at any moment in time can be described by a single number. It's two-dimensional, time versus amplitude. But all the sinusoids in our signal are complex sinusoids made out of a cosine wave in the real dimension and a sine wave in the imaginary dimension. When we add them all together to recover the signal, they form a three-dimensional signal, time versus amplitude of the cosine component versus the amplitude of the sine component. How can we get rid of this third dimension and recover our two-dimensional signal? With only the positive frequency components we found before, we can't, which must mean that there are more frequency components in this signal than we first thought. Additional components that are both equal and opposite, negative frequency components that are the complex conjugates of the positive ones. Now, when we add them together, not only does the imaginary dimension cancel out, but the extra energy stored in the real dimension of the negative frequency components adds to the energy of the positive frequency components. We have found our missing energy, and this is what the full spectrum of our signal looks like. So let's review what we've learned so far, and use it to build an algorithm for the Fourier series. A signal, x of t, can be built out of a sum of sinusoids, each sinusoid with a different magnitude, mn, frequency, fn, and phase, phi n. In periodic signals, the frequencies of those sinusoids are all integer fractions of the period of the signal, so the frequency term fn can be replaced by the term n over p, where p is the period. But what is n, and what is its range? N is the index of the frequency. Our signal has a period of 1 second, therefore p equals 1, and it contains frequencies in the range of minus 20 kHz to plus 20 kHz, so n ranges from minus 20,000 to plus 20,000. However, signals aren't necessarily limited in frequency like this. For example, a true square wave contains very, very sharp instantaneous changes. The frequency of these changes is infinitely high, so if we're to generalize the Fourier series for all signals, n must range from minus infinity to plus infinity. But each sinusoid can be broken down into a sum of cosine and sine waves, with the same frequency, n over p, but different amplitudes, an and bn. What the Fourier series helps us find is these amplitudes for each frequency. For the amplitude of the cosine component, an, it multiplies the signal by a cosine wave at the test frequency, n over p, and integrates the result over one period of the signal. This gives a score for the cosine component, which is proportional but not equal to the amplitude of the original cosine component within the signal. Because we are integrating over one period of the signal, to make the score equal to the original cosine component's amplitude, we have to divide the score by the period of the signal. Similarly, to find the amplitude of the sine component Bn, it multiplies the signal by an inverted sine wave at the test frequency, n over p, and integrates the result over one period of the signal. This gives a score for the sine component. Again, we have to divide by the period to make the score equal to the original sine component's amplitude within the signal. Now, these two separate operations can be combined into one equation using complex numbers, by multiplying the sine component by I, the square root of -1, which rotates it into the imaginary dimension. But Euler gave us Euler's formula, which means we can replace the cosine and sine functions with the complex exponential function, like this. This is the equation we use to find the Fourier series coefficients. So the Fourier series enables us to find the frequency spectrum of a periodic signal. But most of the useful signals we encounter are not periodic. They don't repeat themselves. This whole lecture is a kind of signal, and although I hope you're finding it interesting enough to watch it at least once, I doubt you'll want to watch it over and over again till the end of time. Therefore, the Fourier series would not be able to find the frequency spectrum of, say, the audio track of this lecture. For that, we need the Fourier transform. What we now call the Fourier transform was not the idea of one single person, but was an evolution of the ideas that Fourier laid down, driven by a long list of mathematicians whose work in other fields, not necessarily related to the Fourier series, fed back into the development of harmonic analysis and the understanding of continuous functions. The main problem with the Fourier series is that it builds its signals out of sinusoids. Sinusoids are repeating signals. Any signal you build out of repeating sinusoids will itself repeat, won't it? Is it possible to build a non-repeating signal out of repeating sinusoids?